The goal of this video is to outline a simple computational approach to solving initial value problems that involve first-order differential equations. I want to accomplish this goal by focusing on a problem that, in some respects, will be familiar to you. I want you to consider a particle traveling through one-dimensional space. Suppose the velocity of the particle is a function of time t and of the particle's position s. To keep things concrete, we'll say that function is f of t of s, and we'll set it equal to 2 times s plus 3 times t. Given that the initial position of the particle is 1 unit from the origin, let's find a model for its position at any time t. Based on your experience in previous courses, you might not be surprised to find out that we can restate the problem using a first-order differential equation. Specifically, we look to find a function s of t that satisfies both the differential equation, ds by dt is equal to 2s plus 3t, and the initial condition, s of 0 is equal to 1. The initial value problem involves a linear differential equation, and so we could try to use the procedures introduced in earlier videos to solve it. If we did, though, we'd run into trouble with the definite integral that's a key part of our recipe. Your friends in other calculus courses will know of integration techniques that can be used to show that the solution to the problem is exactly this. But short of taking the time to learn more about integration than we probably want to, what else can we do to attack the problem? I'll propose that we could compute a solution, or at least an approximate solution, by trying to project where the particle will be at various times in the future. For instance, we know where the particle is at time 0, so we could ask, roughly speaking, where do we expect it to be at time t is equal to h? Well, the position of the particle at time h is s of h, and this in turn is equal to its initial position plus the displacement that occurs between time t is equal to 0 and time t is equal to h. We can approximate that displacement by multiplying the particle's known initial velocity by the elapsed time. Doing so gives us an approximate location equal to 1 plus 2 times h units from the origin. In other words, 2h units to the right of where it began. Next, we could ask ourselves, where do we expect the particle to be after another h time units have elapsed? Again, roughly speaking. Using the same idea as before, we say that the particle's position at time t is equal to 2h is its position at time h plus a displacement. This in turn is approximately equal to 1 plus 2h plus its velocity at time h multiplied by h. Plugging in our approximation leads us to this, 1 plus 4h plus 7h squared. The particle is now even further to the right than it was at time h. We can continue like this, stepping forward in time by h units until we have enough data to get a good sense of what the solution to the problem looks like. The method might seem to lack an element of sophistication, but it's better than having no answer at all. The method that I've proposed is well known and has a name. It's called Euler's method. Despite the pronunciation, it has nothing to do with failing to appear in the NHL playoffs. The method is actually named after the famous mathematician Euler, who studied this and so many other problems in mathematics. Now that we know the method has an official name, let's review the more step-by-step explanation of how it works in general. Suppose we're looking to use Euler's method to find a particular solution to a differential equation like this, that also satisfies an initial condition like this. And suppose we want to state the solution for times between t0 and t final, or tf. Step 1 in our solution involves dividing the interval t0 to tf into capital S identical subintervals. The width of each subinterval is calculated as h is equal to t final minus t0 over capital S, and we focus on the right endpoints of each of these subintervals, t1, t2, and so on up to t sub capital S. You'll notice that t sub k is equal to the initial time t0 plus k times h. So, t sub capital S is synonymous with t final. Step 2 involves determining u at time t sub 1. We do so by evaluating the right-hand side of the given differential equation using the initial condition, then multiplying by h and adding the given value to u at time t0. Simplifying the previous line leads us here. Step 3 is really a bunch of steps repeated over and over. We calculate u at time t sub k for k from 2 to capital S using the following formula. Once we've calculated u at time t sub capital S, we move on to step 4, which involves reporting all the data we've generated. We can include the given initial condition here. We can also imagine plotting these data to get a visual sense of what the solution to the differential equation might actually look like. Now let's turn our attention back to the example we started with, and let's solve it in a systematic way using Euler's method with capital S is equal to 4 subintervals. For illustrative purposes, we'll restrict ourselves to times t between 0 and 2. We'll also keep in mind that we can use the known solution as a check on the one we generate through computation. Now I'm reluctant to carry out my calculations by hand, mainly because it's tedious, so instead I'll use a computer. In fact, I'll just use a simple spreadsheet to pull this off. Here's what I've got. One column labeled T and another labeled S. I'll just add the information given to me by the initial condition and I'm ready to go. Step 1 involves establishing the subintervals and finding their respective right-hand sides. I know I've got an interval of width 2 and I want 4 subintervals. So each subinterval will be of width 2 over 4 or 0.5. This means that in addition to t is equal to 0, I'm thinking of times 0.5, 1, 1.5, and 2. Step 2 requires me to fill in cell B3. I can do this by A, evaluating the right-hand side of the differential equation using data in the previous row of the spreadsheet. B, multiplying the result by the width of a subinterval, 0.5. And C, adding the whole thing to the previous value of S. So at time t is equal to 0.5, I predict that S will be equal to 2. For step 3, I just repeat the same basic thing over and over again, always referring to data in the previous row as I go. This is where formula copying comes in handy, as you can see. So we have our data table, and we're ready to plot it. In fact, I've already gone ahead and created a plot here. We've got position S on the vertical axis and time t on the horizontal axis. The numerical solution we just computed is presented as dots connected by a dashed line. For comparison, I've also plotted the exact solution as a solid line. Perhaps the most striking feature of the plot is that the numerical solution we computed using Euler does not match the exact one. What's more, the mismatch gets worse as we move from left to right on the t-axis. I suppose the error is to be expected, since we knew all along we were approximating. Essentially, we've replaced a continuous function with discrete values, and since Euler's method is iterative, error accumulates as the argument of the function grows. Still, the fact that we're so far off by the end of the time interval is a bit unsettling. We might therefore wish to find some way of making our approximation better. Thinking back to our experience with Riemann sums, it seems reasonable to suggest that dividing the interval into a greater number of subintervals could improve our situation. The suggestion, it turns out, is a good one. We see that the approximation is better when we have S is equal to 8 subintervals of width h is equal to 0.25. And it's substantially better with capital S is equal to 64 subintervals. But even here, we still see the effects of compounding error dragging us down. So, there are bound to be errors when we apply Euler's method, but our situation will be improved by taking more and narrower subintervals. Of course, more subintervals means more computation, which is undesirable for other reasons. In practice, we aim for a balance between reducing error and keeping the number of calculations we need to perform reasonably low. Let's recap before wrapping up. We described a simple numerical method for solving first-order differential equations when also given an initial condition. Using an example, we saw how to implement this simple method called Euler's method on a computer. Though we only touched on implementing the method with a spreadsheet, I'll likely require you to use more sophisticated approaches as the course goes on. Next, we saw that, perhaps unsurprisingly, there was error associated with the solutions generated by Euler's method, and that these errors compound. Finally, we saw that we could reduce the error by increasing the number of subintervals included in the method. At this point, you should be able to do a few things. First, you should be able to describe the steps required to apply Euler's method, and you should be able to implement these on a computer. Second, you should be able to identify sources of error associated with Euler's method and explain how their effects might be reduced. Finally, you might also now consider abandoning any preconceptions you had about math always being precise and exact. Clearly it isn't. Sometimes we just need to buckle down, compute, and get the job done. Remember, this video is only the tip of the iceberg. Be sure to complete the reading and do the exercises. Before you know it, your computational game will exceed that of any Euler around.